Yes. All right, folks. So today's discussion again will continue yesterday's discussion with volumes. So today we're gonna take some other approach to these volumes. We're gonna calculate a different type of thing that can be done by the method called the method of shells. So here's what I'll say to you. All right, let's give an example. Let's see what we did yesterday. So somehow I have this thing popping up here. All right, so let's see what we did yesterday. Recall, folks, recall from yesterday. We had a situation like this. We had something, and we rotate that thing, a graph here. We rotate that above the x-axis. So if we rotate above the x-axis, we're going to get something that looks like a pot here, right? So this is going to be our thing rotated above the x-axis. Then we calculate this volume. This volume, remember, was calculated if this is y equals f of x here. The volume was calculated simply by the formula integral from a to b. A and b would be points here on the axis at the end points. A to b, pi times f of x squared dx. So that was the formula. And I said with this formula, you'll go really far, but most of the problems are like that. Now in today's lesson, we are going to move on to section 5.3, and we'll do volumes. I apologize, folks. I don't know exactly what happens here. So let me see if my board was saved. Oh, my board is gone now. All right. Okay, that's a bummer. Okay, so let's see. Am I recording now? I apologize, folks. So I don't know why it keeps interrupting. Oh, I'm still recording apparently. Okay, but I don't see my board. So, there we go. So let's do that again. So today, I'm just going to write the title here, 5.3, volumes by cylindrical shells. All right, and what are we looking at? So again, yesterday we did this. I just have to start this again. We had this situation. We had something like this, and we said we had that and that, and there we go. So we had y equals f of x. The x-axis, rotation above the x-axis, the y-axis here. So I'm just gonna hurry up a little bit here to hopefully we don't get any more disconnections. Here, the volume here we said was integral from a to b. A and b were here of pi times f of x squared dx. All right, so that was the yesterday, and today I'm going to take the exact same situation, but look here today, folks. We're gonna take something, and something like that. This is a function, right, from a to b, and I am going to spin this above the y-axis. Now this is again something of a situation that you will. Oops. Okay, so if we rotate above the y-axis, you'll get something like this one here. So you get the following type of shape. So let me just imagine that you have two things like that, and over here what you have, folks, is this cylinder drilled inside the inside the shape, because remember that we took the graph only from A to B, so A would be here and B would be here, and we only span this area above the y-axis. So the y-axis will be somewhere here. So this is the y-axis. All right, so we span that thing and we get this area about the cylinder, this volume that is, and we want to calculate that volume. So we did discuss this yesterday in the context of spinning above the x-axis. Now, when you spin above the y-axis, for whatever reason, they want to make you believe that this is a different situation from the one yesterday, and it is in some way. But as you know, you always have the possibility to switch the x and the y-axis. And the reason why they don't say in the book do that, rather learn a new formula, is because this time around, folks, if you switch things about, if you switch the x and the y-axis, the graph that you have here switches too, but it doesn't switch to the graph of the function f, so it switches to the graph of an inverse. And sometimes the inverse is not so easy to find. So in order to not go through that pain, what they explain in the book, there's a simple way, independent way of doing things here by doing the following things. So, so first of all, let's assume we're doing when we let's assume we slice up this solid with a horizontal slice, right? We get a horizontal slice out of this. This looks like a pie if you want, with a hole inside, right? So if we slice it up horizontally, we're gonna get two circles, right? So one will be the interior circle, and the other one the exterior circle. And the radii of these circles are very easy. So the radius of the interior circle is A, and the radius of the exterior circle is B. And there's a value x here between A and B. So if you want a circle between these two, then you are going to look at a circle of radius x. And now what they tell us in the book, and this is why it's called the method of shells, they tell us, you know what, if you lift yourself to a height of f of x, remember the graph of f was something here, then you get a small slice, a thin slice, thin vertical slice along this circle that I'm going to color that with red. So you get this circle here, let's say. You get this thin slice along this circle. So let's say it's right above it. So let me make it about equal. All right. And if you add up the areas of those thin slices, which they make them a little thicker, so make them into what's called cylindrical shells. If you add up those areas, then that's going to give you the volume of this pie that has its core scooped out. So that will take us to the following formula. Now remember that adding up a bunch of things between A and B, these circles have a radius between A and B, that amounts to saying an integral from A to B. And if you calculate the area of the cylindrical shell here, this cylindrical type of shell, that area is 2 pi x. So that's the diameter. The circumference of the base circle here times, and then there's going to be f of x in space. So that's the height of a cylinder. So that's the exterior area, and this is the thing that you want to add up. And this formula is going to give you the volume. So the volume in this case is a volume of revolution about the y-axis. this is the story that we're working on here. So that's exactly the formula that we learned today. And luckily, there was no more interruptions. So at this point in time, we can say, well, we have covered everything we really need in this class. So that's the last thing that I want to say from this class. I'll probably do a little bit of discussion of work, as one last lesson, but this is the last sort of important concept. And the rest of the hour, so it doesn't have to be a long lesson again, because it's not going to be something that I'll focus on in the coming lessons. And even in calculus 2 or calculus 3, you probably will see so you will most likely in calculus 3 will see a better method of calculating these. So what I'm going to do here, I am going to calculate a few. I'm going to do a few examples from the book calculating these kind of values. So this is the method of shells. All right. So now we are going to, by the way, the previous method, the method we learned earlier in the previous lesson, is called the method of disks and washers. We saw why disks. So because it's slices are disks when you rotate above the x-axis. So I'm not going to worry much about that. Essentially, the two formulas are just the one version of the other. So it's just you have to be careful when you set up your problems. So I'm going to do a bunch of problems from the book this time around. So I'm going to start with number 3. So again, for the rest of the hour, we're going to do a bunch of examples here. Number 3 of section 5.4. And number 3 is, there we go. So y equals the cube root of x, y equals 0, and x equals 1. This is the region that we want to rotate above the y-axis. So about the y-axis, let's draw a picture. Let's see what it looks like. So very quickly here. So here's what that looks like. We got x equals 1 over here. It's a vertical line. We got the cube root of x. Now the cube root of x will be something like, so it's going to have a part here, and it's going to have a part something like this here. So it's going to go a little bit, yeah. So this is the region, and I think this is a y equals 0 is the x-axis. So yeah, so this is the region that we spin about the y-axis. So when we spin about the y-axis, this region, what we're gonna get will be something like, and I'm gonna draw that. Maybe I should draw that with a different color. Oops, nope, not that. Red. All right, so I'm gonna draw it with red. So what we get here really is this thing that really looks like a funnel. So I can't draw it very well, but there we go. It looks like a funnel thing, folks. But the thing is, you're not calculating the volume of a funnel, but rather the volume. So let's assume we have this cylindrical box of ice cream, and we scoop out the shape of a funnel. So that's the remaining area, that's the remaining volume, that's what we calculate. And the calculation will not be difficult. So the volume will be an integral from, and as I said here, you just have to be careful to set up. The integral is 0 here, the left-hand point, there is 1, the right-hand point, so 0 to 1, 2 pi times f of x. F of x is the cube root of x times 2 pi, 2 pi times x, and then times f of x, which is the cube root of x. So we said earlier, see here, 2 pi x times f of x dx. All right, so this is the formula that we want to evaluate is dx, and right now everything else is just a bunch of simple calculations with antiderivative. So the whole thing is really 2 pi times x to the 1 plus 1/3. Folks, I apologize. I don't know what's going on here. So uh, my work keeps being, my computer keeps going on and off. I don't know what's happening. So I'll try in good faith here to keep this going. Luckily, it's the last. Yeah, yeah, I know it crashed. They came back. All right, folks. So I'm gonna keep going on in good faith here. So my kids are complaining that the Wi-Fi is not working. Um, so so again, let's go back to this thing. We are looking at okay. So number. All right. So I'm gonna redraw that thing. Um, so we were really calculating. Let me just calculate quickly here by hand so we can finish up that problem at least. So integral from 0 to 1, 2 pi, it was x times the cube root of x. I remember the problem, so shouldn't be a big deal. And we were here at really at the antiderivative of the calculation of integral 0 to 1, 2 pi times x to the 4/3 dx. And that, folks, is something that we can calculate easily. So the antiderivative of 2 pi x to the 4/3 dx is, so you write it quickly, is 2 pi times x to the 7/3, 3/7. So this is going to be from the evaluated from 0 to 1. So if you evaluate from 0 to 1, plug in 1, you'll get 2 pi times 3/7 times 1, and then minus 0. So it's going to be 6 pi over 7. This is going to be the desired volume. I apologize for the often interruptions. I don't know why the connection is unstable today. So we're going to do as much as we can. I guess at the next interruption, I'm probably going to wrap things up. Okay, so let's stop here with this problem. Let's do another example here. So number 4 from section 5.4, 5.3. Apologize. All right, says you got y equals x cubed, and then y equals 0, x equals 1, and x equals 2. And you're trying to calculate the what happens, the volume of a thing, the solid obtained by spinning this above the x, the y-axis. So let's see what happens. All right, so we have this thing, x equals 1, x equals 2, x cubed. X cubed is something like this, not exactly, the graph here is not very precise, but you get the idea. So this is x equals 1, this is x equals 2. This point here is 2 comma 8, and this one here 1 comma 1. So again, you're spinning this thing above the y-axis, and when you do, what you're gonna get is really gonna be something that looks like this. I'm gonna draw that with red, so hopefully this there we go. So all right, so we get this thing here, and again we get something like that, and remember that we're actually cutting out this part here, so we cut out this part, and we will be left with the all right, with just the So imagine that you have folks a bowl full of ice cream, a cylindrical cup full of ice cream, and you're scooping out. You're scooping out. Simply take a scoop out of it, from the top. Then you get the shape here, and then you also clean in the middle, clean out a cylinder there. That's going to give you the remaining parts of the volume that you want to calculate is this. Again, it can be set up very easily as an integral from, I'm sorry, not from 0, from 1. Come on, 1 to 2. So it goes from 1 to 2, 2 pi, 2 pi x times, and then you get the desired f of x. So f of x, folks, the function that we're looking for here is this one, x cubed. So so when we got that, we're going to write x cubed here, dx. This is really going to be a simple integral. So it's 2 pi times x to the 4 dx, and that is going to be the antiderivative of 2 pi x to the 4. I can even write it directly. So 2 pi over 5 times x to the 5th, from x equals 1 to x equals 2. Subtract these things. So 2 pi times 2 to the 5th is going to give us, let's see, 2 times 2 to the 5th is 2 to the 6th, which is 64 pi minus, and then you subtract 2, so it's 62 pi over 5. So that's the calculation of the antiderivative. All right, so we did a couple of problems again. Recognize the form 2 pi x and then f of x over here, or y of x if you want. In this case, this is the format for this particular type of problem. And finally, I'll do one more and I'll finish up there because I don't want to push too much. We already had enough trouble here with the technology. I don't want to crash on this particular any more problems. So so number 6, hopefully we're going to be able to keep a connection here. Number 6 of 5.3 is the following question. So so we have the curves y equals 4x minus x squared. And the other one is y equals x. All right, so we got these two curves, and again, we want to spin about the x-axis. Now, let me show you what this looks like in real life in Canvas, I'm sorry, Desmos. So we're going to open Desmos here. All right, I'll share that with you folks. So here's what we have. So one curve is y equals 4x minus x squared. All right, so we get this particular parabola, and the other one is y equals x. All right, you can see that the area between them is this one here. So it's one curve at the top and the other one at the bottom. So so what's happening here? So we are going to spin this thing above the y-axis. What's happening? Well, one of the curves. So so again, if we do the intersection point is at 3, 3 over here, as you can see. So if we do the line x equals 3, so we need the picture here to kind of figure out what the thing is. When you spin out, you're going to get this thing that looks like a cone, which is cut out by the straight line, this one that I'm going along. So so this is going to be something that's spinning. And then there's the top curve that also spins, and it gives us some other shape over here when we spin out. So this top equation, will give us a volume, a full volume, and then we're going to subtract the volume under the bottom equation. So that's kind of what's added as a plus to this particular type of problem. So this particular type of problem, folks, and I'm going to go back and I'm going to draw a picture there. So we saw that the picture looks like this. I'm going to draw a picture. Hopefully it doesn't get disconnected. That would be a disaster. All right, so here's what we do. We have these lines here. Oops, not that. So let's undo that, and let's do something with blue, like it. Oops, not blue. Blue like. Hold on a second, folks. No, let's draw, but let's draw with blue. There we go. So it's going to be something like this. Okay, this is y equals x. All right. And finally, y equals 4x minus x squared. We saw it goes, let's do that with red. So it goes something like this. And we figured out that this point, the corner over there, is this one here is 3, 3. And that's going to be 3 over here, 0 over here. That's the area, and that's the one that we're going to spin about the y-axis. So that's kind of a thing here. So folks, it's not an area problem; it's a volume problem. So now the volume problem, luckily. I don't really know what's going on here. There's a lot of things popping up on my screen. I apologize. So the volume that we want to calculate, and somehow this one became smaller. So there we go. What's happening here? All right. So there we go. I don't know what's happening here. So the volume that we want to calculate, folks, is going to be an integral from 0 to 3 2 pi times x times, and I'm going to say the top equation, which is f of x, right? So which is 4x minus x squared, and that's one part of the volume. So that's going to be whatever happens when you spin out the area under the red curve. So this area when you spin out above the x-axis, and then minus, so what we have to say, minus the same type of thing, integral from 0 to 3, 2 pi x times, and then we subtract the volume under the blue curve. So that's going to be 2 pi x times x, because the blue curve is given by y equals x. That's the formula. So that being said, we're going to calculate this as follows. The first integral is going to be an integral from 0 to 3 of 8 pi. Let me calculate that. 8 pi times 8 pi times 2 pi times 4, 8 pi times x squared, minus, and then there's 2 pi times x cubed. And then we can subtract this one from here, which is another 2 pi times x squared dx. So we put them all together in the same big integral, which is an integral from 0 to 3, folks, of 8 pi times, okay, so 8 pi x squared minus 2 pi is 6 pi x squared. All right, minus 2 pi x cubed. All right, dx. The antiderivatives, again, very simple. So the antiderivative of 6 pi x squared minus 2 pi x cubed dx is really nothing but, for here, 6 pi times 1/3 x cubed minus 2 pi times 1/4 x to the 4th. So 1/4 here. So that simplifies a little bit, and that's going to give us 2 pi x cubed minus 1/2 pi x to the 4th. This is the antiderivative, and the integral here really is, we just have to plug in 3, because if you plug in 0, we get 0. So plug in 3, we end up with 2 pi times 3 cubed minus 1/2 pi times 3 to the 4. So this is going to be, okay, so, okay, so that's going to be, well, a large number. So let's figure out 3. Okay, so um, 3 cubed, 27 times 2 pi minus pi minus 3 pi over 2, which is just going to be pi over 2. 27 times pi over 2, so it's 27 pi over 2. Oops, sorry about that. There we go. So 27 pi over 2. So that's going to be the final answer for this particular volume. And we finally figured out the volume. Now I am going to, okay, so I am going to, well, let's see, how much time do we have? We still have some time, and it looks like the connection is stable. Okay, so I'm just going to point out one more thing, and I'll finish up there. I'm just going to point out the following thing, folks. Over here, he says, use the method of cylindrical shells to find the volume of a solid obtained by rotating about the x-axis. So, so here's what we do when we rotate. When you rotate about the x-axis, if you want to use cylindrical shell, so we're kind of going backwards. We didn't even do the other one. We just discussed briefly about the other one. So I'll say with cylindrical shells. So make sure, so you can follow this method. So switch X and Y in the problem, and then make the problem of rotation, and then transform the problem. Transform the problem into a problem of rotation about the y-axis. And for rotation about the y-axis, you have that standard formula. The volume equals 2 pi x f of x. You integrate that from whatever a to b. All right, so this is all I'm going to say. I'm not going to do an example. In the book, there's a bunch of examples with this, but I'm not going to do an example because, again, I don't want to confuse you. And the reality is, these are so peculiar, so I would say very extreme in a way. These type of problems that it's not really worth spending time to do these kind of things. I mean, this is something that I would rather save time and do something else. So the conclusion of this lesson is that I'm going to stop sharing here. So the conclusion of the lesson is, folks, this is something nice to know. Most likely, I'm not gonna put this particular type of problem, at least the more challenging one. I'm not gonna put that on the test. So on tests, I usually do the following thing: I give a volume question. But I give a volume question that can be done both ways, both cylindrical shells and washers, the method earlier. And I let you choose which one to apply. So learn one of the two methods, and if you know the washers, the one in the previous lesson in 5.2, that's good enough. You should be able to do the problem. Or if you know this other method, then you should be able to do the problem. But again, be careful. So if it says rotation above the x-axis, make sure that you switch x and y to make it a rotation above the y-axis, and then apply cylindrical shells. So I'll do that on a test. I won't try to ruin your grade with these type of problems. You are going to come back to those if you take calculus 3 again. There's much better ways there to set up integrals. For example, what we just did here in the context of cylindrical shells is really setting up polar coordinates in calculus 3, and that's much easier to, it's a much better concept. At least I have a much easier time visualizing that versus, kind of learning a formula that was derived in a very special way. So that's what I'm where I'm gonna stop my recording here.